Morning.
Good morning, ma'am.
In the last class, we discussed problems based on finding the impulse response of the system. So, from the given block diagram, we should apply the rules of cascade connection and series connection depending on the structure. So, we apply the rules and then we find the total impulse response of the system. I had given one homework problem that we will discuss later. So today I start with a new topic, relations between LTI system properties and the impulse response. So let me give the difference between this topic and the topic in the second module. In the second module, we discussed the properties of the systems. So like we have discussed causal property, memoryless property, linearity property, time invariance property, etc. So we discussed the properties of the systems in the earlier module. Now in this module, I am going to discuss the properties of the system in terms of impulse response. So let me clear in turn with the help of the output equation. So in the previous module, I can say I was explaining all the properties of the system in terms of output equation. In terms of output equation. But in this module, I'm going to explain the properties of the system in terms of impulse response. So that is the difference between the properties in previous module and this module. So in previous module, we explained the properties using the output equation, and here we are going to explain the properties with the help of impulse response equation. So we have some properties common between the previous module and this module, and we have some new property also in this module. So I can say the common properties, what I can say is in from previous and this module, memory property is a common property, causality is a common property, um, stability. Stability is also the common property. So along with this properties, we are going to discuss uh, the new property called step response, new property called step response, and one more is invertibility and invertibility. Even in the previous module also we discussed invertible, but along with invertibility, we are going to discuss deconvolution. Deconvolution. So you know what is convolution? We have discussed enough about the convolution. Convolution is nothing but performing the operation on two signals x of n and h of n such that I will get the output y of n. That is convolution. Deconvolution is nothing but the process of retrieving the signal x of n and h of n back from the output signal y of n. So it is the opposite process of convolution. That is deconvolution. So these are the properties which we are going to discuss in this module in terms of impulse response h of n. So now let me start with the first property. You no need to write anything here. I will forward this. Already I have shared this PDF to the classroom app. So just listen now. Later you can copy this topic in your notebook. So memoryless LTI system. So I can say the definition is same as previous module. What is the definition? Definition is memoryless means the output should depend only on the current input. Okay. If the system has a memory, then the output depends upon the past input as well as future input, like that. Since it does not have any memory, my output depends only on the current input. The definition remains same. And I can give the output of the discrete time. I'm taking discrete time LTI system. Later, I will write the equation for the continuous time LTM system also. So y of n is equal to h of n convolution with x of n. We all know very well. So I can expand this formula, convolution formula, as summation k equal to minus infinity to plus infinity h of k x of n minus k. So I told in number of classes, it is our wish. Any signal we can keep constant and any signal we can perform shifting operation. So in original formula, we always take summation with x of k, h of n minus k. But here, my h of k is the main parameter in this property. So h of k I will not disturb. H of n I will take it as h of k, and this x of n I will just perform the shifting operation. So the formula becomes summation k is equal to minus infinity to plus infinity h of k x of n minus k. So any signal we can keep constant, any signal we can shift it. So for my convenience, I am keeping h of k constant because h of k is the main parameter throughout the properties. So we do not disturb h of k. Only x of n, we will take it as x of n minus k when we expand the formula. Now the next thing is I want to expand the summation. So left hand side I know it is y of n. Y of n is my left hand side, which is equal to, my summation is from minus infinity to plus infinity. So if I take the scale, it is from minus infinity to plus infinity. So I want to take some range of n. So what I'm doing is, as per my equation which is written in the screen, I'm taking n value from minus 2 to plus 2. So 0 or minus 1 here, 0, 1, 2. Okay, so now when I take the initial k value as minus 2, let me expand this summation. So h of minus 2, x of n minus of minus 2. So it becomes x of n plus 2. Similarly, when I substitute k equal to minus 1, I will get h of minus 1. X of n minus of minus 1 becomes x of n plus 1. And similarly, n is k is equal to 0. When we substitute k is equal to 0, this h of k is h of 0 into x of n. So this is your middle range, middle value, middle term, I can say. And later on, I will substitute k equal to 1, and later on, I will substitute k equal to 2. So it is my wish I can take the range from minus 2 to plus 2 or minus 4 to plus 4. If you take bigger numbers, you have to write the expression. The expression will have more number of terms. So just for our convenience, we take the limited range and we just expand it. So what I want to convey here is, you all know very well, you know how the impulse response in general. Impulse response will be having the amplitude or the sample only at the origin, only at the origin. So I'm just showing here, only at the origin. Okay. So at all other places, I do not have any amplitude. So I can say this is h of 1, h of 2, h of 3, and this side it is h of minus 1, h of minus 2, h of minus 3. Okay. So I can say my first term h of minus 2 into x of n minus 2 becomes 0. You know the reason, h of minus 2 is 0. Similarly, h of minus 1 into x of n plus 1 is also 0, and h of 1 into x of n minus 1 is also 0, and h of 2 into x of n minus 2 is also 0. So the only term which will be present in this equation is the term which I am highlighting now. The term is h of 0 multiplied with x of n. So using this concept, I can say in this h of 0 into x of n, if you see, the output, the output depends on the current input. The output depends upon the current input. So because of this reason, I can say this system is a memoryless system. So as per the statement, what I told, the memoryless system is a system in which the output depends only on the current input. So I proved it here. When I expanded the formula of y of n, I proved it. The output y of n is depending only on the current input x of n. And you can ask me the importance of the impulse response here. So the importance of impulse response is, with the help of impulse response only, I eliminated all other terms here. With the help of impulse response concept only, I eliminated all other terms. So I could only retain this term h of 0 into x of n. So here the impulse response plays important role. So using this concept, I'm going to write the output for the property. So let me show you the property, how the property is. So you can write this property in your rough notebook, because when we solve the problem, I will ask you the formula. So as per the previous equation, I got h of uh, 0 with x of n. This term only was enabled. So I need to write this h of 0 in general case. So h of 0 in general case, I can write it as h of k, which is equal to c multiplied with delta of k. So this is the formula we are going to use in this module if they ask you to verify whether the given system is memoryless or memory system. So you have to use this formula in terms of impulse response. So this formula is in terms of impulse response. Whereas if you see in the earlier module, that formula was in terms of output equation. So the same thing I'm repeated again and again. That is the difference between the earlier properties and this property. So the final conclusion is the discrete time LTI system is memoryless if and only if. So when it is memoryless, then this impulse response h of 0, in general I can write it as h of k. H of k is equal to c. C is a constant multiplied with delta of k. So you know delta of k is also 1. Delta value is also 1. So that's why the impulse response is also 1 at the origin, which should be related to the same type of variable. The same type of variable is delta of k. We all know delta is also having the sample only at n is equal to 0. So here it is k is equal to 0, I can say. So I can relate h with delta, so such that both are representing the same condition. So the formula is h of k is equal to c multiplied with delta of k. So in the same way, I want to write the equation for the continuous time system. So continuous time system, you know very well how to expand the formula. So the expansion is integral minus infinity to plus infinity h of tau x of t minus tau. I repeatedly am telling h of tau I will not disturb, because based on this only I am going to write the formula. So I can disturb the other input. The other input is x input. So h of tau x of t minus tau d tau. So later I want to write the condition for continuous time system also, the formula of h. So instead of expanding the integration, directly I am just writing the equation, because I have just written for discrete time system has h of k, which is equal to c multiplied with delta of k. The same thing I can map it for the continuous time system. So this integration I'm not going to expand like how I expanded for the discrete time. So we can write similarly for continuous time system also. Similarly, I can write the formula for memoryless property. So in place of k, I will replace tau. H of tau is equal to c is c only, and delta of k now becomes delta of tau. So I want you to just write these two formulas in your rough notebook. Suppose if I get the time today, I will start solving the problem also. So that time I will ask you what is the formula to find out the memoryless system. You should tell me h of k is equal to c delta of k. H of tau is equal to c delta of tau. So my conclusion is all the memoryless LTI system simply perform scalar multiplication on the input. So this is called a scalar multiplication. So this memoryless system impulse response, what it is doing, it is performing the multiplication, scalar multiplication on the input. So as per this equation, my left hand side is my output and my right hand side is my input. So if I imagine in that way, I can understand this concept which is written here. All the memoryless LTI system performs. So what it performs? It performs scalar multiplication. That means C multiplication on the input. The input is delta of I. So we have completed the first property called. Next property is causal LTI system. So causal LTI system. We all know in the previous module how to identify the system is causal uh, based on the output equation. So here I am going to write the formula in terms of impulse response. So before writing the formula in terms of impulse response, always the initial step is I should find y of n equation. From y of n equation, if I expand, I will be able to eliminate some term because based on the concept of Cauchy, and from the remaining terms, I will be able to write the formula in terms of h of n or h of k. So here, what I'm doing is first let me define the Cauchy system. You all know very well the Cauchy system depends only on the past and present values of the input. This you know very well, and so since it depends upon the past or present values of the input, so based on this condition, I am going to eliminate some of the terms after expanding my y of n equation. So in the previous memoryless systems topic, I took the scale from -2 to +2. Okay, I took the scale from -2 to +2. So the same equation I'm going to repeat here. So when I expand y of n, so it is h of -2 into x of n plus 2 plus h of -1 into x of n plus 1 plus h of 0 into x of n plus h of 1 into x of n minus 1 plus h of 2 into x of n minus 2. So this equation is similar to the previous equation under memoryless systems. So here, based on the concept of causality, I am going to eliminate some terms, like how I have done the elimination in the previous topic called memoryless system. The same concept I am going to apply here. So when I apply the same concept, my condition is the output depends only on the past or present values of the input. Past or present values of the input. So now if you see here, you should know which is past input and which is present input. So x of n minus 1, x of n minus 2 are the past inputs, and h of 0 and x of n is the present input. Whereas if you see x of n minus 2 and x of n, n plus 2 and x of n plus 1, those are the future inputs. So this we have already discussed enough in the previous module. So as per the causality system, I should not have any equation which has the future values of input. So I will be eliminating h of -2 into x of n plus 2. Similarly, I will be eliminating h of -1 into x of n plus 1. So after eliminating these two terms, I can say my output y of n is now having only three terms, h of 0 into x of n plus h of 1 into x of n minus 1 plus h of 2 into x of n minus 2. So I hope you all follow how I have eliminated the terms here. I have eliminated the terms based upon the condition of causality. So the condition of causality is nothing but the output depends upon the past and present values. So I try to find which is past, which is present, which is future. So the first two terms as per this equation is future. So this will not present in the final equation. So the only equation which I will get is h of 0 x of n plus h of 1 x of n minus 1 plus h of 2 x of n minus 2 plus etc. So based on this, I can say out of these three terms, in turn I know my output y of n depends only on the past and present values of the input. So for that, the condition in terms of the impulse response is h of k is equal to 0. H of k is equal to 0 when k is less than 0. So I am writing the final equation h of k is equal to 0 when k is less than 0. So you can ask me, ma'am, how you have written this equation for causality using the impulse response. So as I said earlier, uh, the h of k is 0. H of k is 0 when k is less than 0. See here, the k is less than 0. That means the k value is -1. Similarly, h of k is equal to 0 when k is less than 0. Here again, the k value is equal to -2. So then what is the contrary to this equation? My h of k value will be not equal to 0. It is not equal to 0 when when k is greater than or equal to 0. So if h of k is not equal to 0, when k is greater than or equal to 0, I can say these terms will be present, because here k is 0, and here k is 1, and here k is 2. So using these eliminated terms, first two terms, I could write my equation. The common equation is h of k will be equal to 0. At what condition? When k is less than 0. So here k is less than 0, that means minus 1. Here k is less than 0, that means minus 2. So the opposite to this equation is h of k will not be equal to 0 when k is greater than or equal to 0. So this is my final conclusion under the causality. So I want you to remember this equation, h of k is equal to 0 for k is less than 0. So I will ask you this equation when we solve the problem in this module. So similarly, I want to write the equation for the continuous time system. So continuous time system, uh, continuous time system, you know how to map it. So let me just scroll the screens little up. So you know how to map it. So k becomes tau, and your here the range of k, instead of k here it is tau, except that remaining everything is same. H of tau is equal to 0 for tau less than 0. So even when I expand the formula of continuous time system, integral minus infinity to plus infinity, h of tau x of t minus tau. So when I expand this integration, I definitely know that I will get my output only when k is greater than 0. Here tau is greater than 0. So instead of writing minus infinity to plus infinity, let me write the integration from 0 to infinity. 0 to infinity, h of tau x of t minus tau d tau. I hope you are all understanding why it is from 0 to infinity, because the negative values I am not getting any output. Because of that reason, I am getting the output only from 0 to infinity. So instead of the original limits of integration minus infinity to plus infinity, I can modify it as 0 to infinity. Similarly, for convolution sum also, the original summation limits are minus infinity to plus infinity, and I expanded the summation. I got to know that I will get the output only from 0 to infinity. So instead of lower limit minus infinity, let me remove that minus infinity. I will start from 0 to infinity. So the formula is now convolution sum, summation k equal to 0 to infinity h of k x of n minus k. So in the exam, sometimes they may give you the hint in the question paper. The given system is a causal system, then find the convolution sum. If they give the given system is a causal system, find the convolution sum. You should not start with minus infinity to infinity. I hope you understood. So you should start with 0 to infinity. If they mention the system is causal, if they ask you to find out the convolution. Stable LTI systems. The definition is same as the previous module definition. The system is bounded input and bounded output. So you know what is bound? Bound means within the range. It is limited. So I can say the system, LTI system is bounded input, bounded output. So in short, we will call it as BIBO stable. If so, when I call the system is BIBO stable, if the output is guaranteed to be bounded for every bounded input. Okay. So if input is bounded, my output also should be bounded. So when it follows this condition, then I call the system as a BIBO stable system. So all these definitions we have discussed enough in the previous module. So I'm going to start with the equation. So you know how to represent the condition of stability in terms of equation. So if input to be a stable discrete time system, then it satisfies the condition. So we have seen in the previous module, so this mx should be between minus infinity and magnitude of x of n. So if the input is bounded, see here this is saying that it is bounded. If input is bounded, definitely the output should also be bounded. So for that, the condition is magnitude of y of n less than or equal to my less than or equal to infinity. So this is same as the previous module equation or the definition for the stable system. So now with the help of that, I am going to derive the equation such that my equation should be only in terms of h. So let me start with the equation of y of n. I am considering only the magnitude part because just now I have discussed my magnitude of y of n should be between my less than or equal to infinity. So because my equation of stability is in terms of magnitude, I am writing the equation, convolution equation. This is the convolution equation in terms of magnitude only. So magnitude of y of n is equal to magnitude of h of n convolution with x of n. So we know how to expand h of n convolution with x of n. So summation k equal to minus infinity to plus infinity h of k, and we are shifting the input signal x. So it is x of n minus k. So and I am going to use a formula. So the formula is actually I have written in terms of plus. It should be product. Okay. If you have inside the magnitude, if you have the product, then that can be written as less than or equal to magnitude of individual variable, product with the magnitude of the other variable. So when you write the notes, don't use plus sign, okay? So it is product. Since we have in the previous equation, we have a product. So the product is inside the magnitude, then I should know how to replace that. So the replacement is less than or equal to magnitude of the first term multiplied with the magnitude of the second term. So the summation is common, which is taken outside. So now in this, I am going to apply the condition of stability. So the condition of stability is if x of n is less than or equal to mx less than infinity, then my x of n minus k, because in this formula my x of input is not in original form, it is in shifted form. Then my shifted version of the input signal should also be less than or equal to mx. So if that is the case, then I can write this x of n minus k as mx. So if I replace x of n minus k as mx in this equation which I am highlighting in here, then my equation becomes y of n less than or equal to, so x of n minus k is now mx. It is bounded, and summation k equal to minus infinity to plus infinity, the left out term is h of k, magnitude of h of k. So now here this equation magnitude of y of n less than or equal to mx less than or equal to mx summation k equal to minus into plus infinity magnitude of h of k, in this equation I can say the output is bounded because it is less than or equal to mx. So it is less than or equal to the condition of the input mx. So since output is less than or equal to the input, I can say if input is bounded, my output is also bounded. So still my work is not completed. I should write in terms of h only. So I can say in the above equation, if you see this y of n is less than mx summation k equal to minus plus infinity h of k. which in turn it is less than or equal to infinity. So here I want to only relate the impulse response with this infinity. I don't want to relate my output to infinity. So I am going to relate these two now. When I relate these two, so I can say the summation k equal to minus infinity to plus infinity, magnitude of h of k less than or equal to infinity. If this mx moves towards the right hand side, it will be infinity divided by mx. So infinity by anything is again infinity. So we neglect this mx at the right hand side. So I hope you are understanding this, why mx is not there in the final equation. So if you see the final equation, you can see in the screen, the final equation is having summation k equal to minus infinity to plus infinity, magnitude of h of k less than infinity. So you don't ask me where this mx gone, just now I have explained. So as per the condition, this mx should be moved towards the right hand side. So infinity by anything is infinity. So I can say the summation k equal to minus infinity to plus infinity, magnitude of h of k is less than infinity. So if they ask you to check whether the system is stable using the impulse response equation, then you have to use this formula. Summation k equal to minus infinity plus infinity, magnitude of h of k less than infinity. So the same thing I am going to write for my continuous time system. My continuous time system, it is minus infinity to plus infinity, magnitude of h of tau, h of tau less than infinity. So we have discussed the condition of stability in terms of the impulse response. So all the previous three properties we have discussed in terms of impulse response. So up to that, so the question is, first order system is y of n is equal to rho, this is rho, y of n minus 1 plus x of n. So they have given the output y of n is equal to rho y of n minus 1 plus x of n, and it has impulse response h of n is equal to rho power n into u of n. They are asking you to check the system is causal, memoryless and bibostable. So based upon this h of n, I will be able to identify whether the system is causal, memoryless or bibostable. So let me uh, find whether the system is causal or not. See, I can say the system is causal. Why? Because my h of n is 0 when n is less than 0. You all know very well, from the given equation, I know that I will be getting the, so if I mark h of n in the diagram, so h of n they have given in terms of u of n. That means I'll be having only at the right hand side. I'll be having only at the right hand side. So when we concluded the causality property, we concluded that h of n will be equal to 0 when k is less than 0. So here again the same condition is applicable. I have the samples only at the right hand side. That means when k is greater than 0 or k is equal to 0, I am getting the output. But as per the condition of causality, I should see only this condition, whether h of k is equal to 0 for k less than 0. Can anybody tell me whether my analysis is correct to this problem? Can I say the system is causal? System is causal. Is it right? Is the system causal? Are you getting any confusions here? So I conclude that the system is causal. So condition for causality is h of k should be equal to 0 when k less than 0. You just see this diagram. From this diagram I have taken from the equation in the question. So the meeting may get disconnected. We will join back and discuss.